Okay, so this is where we had stopped in the last session, right? And
Yes.
so this is the extra line. So there's some column, some number which was not being read as numeric. Okay, and that's why we got that error. So what I'm doing, okay, I'm converting this X to data type float. Okay, NP
Mm.
array. So converting into array, converting. So see, your X will be an array. Okay,
Okay.
okay. So I'm converting into array, and I'm saying that all the values will be of type float. Okay, so
Okay.
there's no chance of X to be anything other than number. And then we are doing same.
Yeah.
OLS, okay, dot y comma x fit summary, and let's run this and see what we get. Okay,
Mm. Count
this
number.
is the summary. Okay, all these things we have seen yesterday. 1 second. Okay, all these things, variance,
Yes.
all these
Bias.
things. Okay,
Mm.
what is new is this one. Okay, this
Uh,
is the result of OLS. Okay, what is OLS? Least, okay, least square method. Now, what is least square method? Least square method, if you remember in your intermediate mathematics class, this is what we did. Okay, least square is how do you calculate the distance? Okay, this says that we have used distance method and we calculate distance using least square. That means your x2 minus x1 whole square plus y2 minus y1 whole square and then square root. Okay, using that
uh,
method it has found dependent variable is y. Model that we had used to make all this prediction is OLS, that is least square method. Date, okay, on which we have run this summary. Time, okay. Number of observations. Number of observations is 50. That means there are 50 rows. Okay, there are 50 rows. Okay, then you have DF. Okay, DF. Okay, DF residual is called degree of freedom of the residuals of the observation. Okay, and this is your number of observation minus number of columns. So number of rows minus number of columns. That is the degree of freedom. Okay, so that's how you get 45. 45 is 50 minus, okay,
Fine.
5 columns.
Mm.
And DF is a degree of freedom of the model, which is number of columns, which is 5.
Columns.
Okay, so this gives you 5. Now, okay, covariance type is non-robust. Okay, this is a new thing that got added here. And then here, R square. R square value is 0.988. Adjusted R square. Okay, what is it? So see, when you have only one x, okay, we talk about R square. But when you have multiple x, okay, in this case we have almost 5 columns, right?
Mm.
So then we do the adjusted R square, and I'll show you later the formula of adjusted R square. It's there in the notes that I have shared. Okay, when you have more than one x, then we also need to study the impact of other x. Okay, and typically your adjusted R square will be lower than the R square. R square is the model that best fit model kind of, and as you keep on adding, okay, so you will get your R square will come down. So generally we look at adjusted R square when you have more than one x, and R square when you have only one x, like in simple linear type. Okay, so in this, since we have 5 columns here, in this case, this is important, not this one. So and typically this will be lower than this. Okay, then you have other things. Okay, this is the F statistics. What is statistics? Okay, statistics is the test that we perform, right? Hypothesis test. Okay, so this is the probability. Okay, when you see this will be a probability here. Okay, F statistics. Okay, this is the probability of F statistic. Okay, so this probability here, okay, is the probability that you would get above this statistic. Okay. So it is almost equal to 0. And this shows, F statistics shows the model that we have created, how good it is a fit. Okay. And this is actually calculated using the mean squared error. Okay. Divided by, okay, the mean squared error of the model divided by mean squared error of the residuals of the error itself. Okay. So how far, okay. So here the larger the value, okay, not so good model you can say. Okay, we want this value to be smaller. Okay, so when you're comparing two models, okay, or we are making it better, and that's what we'll do today. We'll make it better. This value should decrease. Okay, then uh, uh, these are all AIC, BIC. Okay, AIC stands for ACIC information criterion. BIC stands for Bayesian information criterion. These are all like um, they're all it talks about how well your model has fit. Okay, higher this value, they measure in terms of penalty. Okay, so they put penalty if your model is not performing well. Okay, so all these are important metric. Okay, but for us, for simplicity, we'll just look at adjusted R square. Okay, this is important. Okay, but then yeah, the when you want to get deeper into the performance, these all metrics will will tell you that how good your model is. Now coming back to the step here, this is the key. Okay, this is what why we have done here. See, apart from that, you also see here skewness, okay, kurtosis, all those things are calculated. Okay, now this is the actual analysis. Okay, and this is why we have run. So this is your coefficient. This is your coefficient. Coefficient means 3464. Okay. Now, okay. So 3464 into x1 plus 5067 into x2 plus 7182 into x3. Okay. These are coefficient, and this is the standard error, plus or minus. This also, of course, the term is error, it should be less, right? You expect it to be as less as possible. Okay. Now, if you see here, this is a T statistic. This is F statistic, T statistic. Again, to test how well your X1 is impacting your analysis. One way to do is look at this P value. Okay. Now, P value, what did I say? Okay. See, in order to do any work, any job, right, we have to reject the null hypothesis, isn't it? Otherwise, if null hypothesis is there is no impact, there is no impact. So you run this model on, you select this column or not, it has no impact. If it has no impact, then why do we select it, isn't it? So typically your model should be, okay, or your p-value should be less than 0.05. That's when we say at 95% confidence. Okay. So your p-value should be less than 0.05. So remember this. Okay. Now in this case, you see only 3 of these values have p-value less than 0.045.
0.04.
Okay. Or first two is higher, which means this first two model does not play much important on your analysis. But we cannot just say like that. There's a process we have to follow. Okay. Now, the process here is which all X to select, right? We ended up getting 2 columns for region and 3 columns for your R&D spend, admin spend, and marketing spend. Now, out of these 5 columns, okay, so we have calculated fine, but okay, the question remains, are all these 5 columns important for the analysis? Isn't it? So as I said, told you yesterday, experience, if you think that that all 5 are important based on your experience, you will go with experience. Then you will not do the OLS summary. But now let's say you want to really see which one is impacting. Clearly, if you see this data, okay, there are columns which probably are not important. Okay, 48% means you're only like 51 or 52% confident. This is like 70 or 60, no, 70, right? 71, 72% confident, right? So we don't go by that. In testing, 50-70% confidence is very low. Okay, we have to be 90-95%. Okay, sometimes we go by 99% confidence. Okay, only then we add a feature, right? You're developing a product and you're only sure about 80% that will work. Better not add that. You have to be 99.95% confident in order to add that feature. This is what p-value tells you. Now, so we need to remove it, right? It's called selection of your independent variables. Okay, how do you select independent variables? So generally, as I said, first experience. Okay, then there are there's one process where you say, okay, I don't care, let me add everything. Okay, I don't care if my accuracy is bad. Okay, so see, two things will happen. One, if that x is not important, it's going to reduce your r square value, isn't it? Okay, and so it's not going to give you accurate results. Second thing is, as you have more x, your model will take more time to run also, so complexity increases. Here we have only 50 rows, but in real life you will never have 50 rows. Okay, 50,000 probably will be the minimum that you'll be dealing with, right? So we need to make sure that we select the right features. Okay, we call them as feature. Okay, or so that's why this process is also called as feature selection. Okay, so input variables, features, independent variables, they are all same. Okay, they are referred by these names. So the process here is feature selection. So how do we select the feature? Okay, so there are method like backward selection. Okay, backward um, uh, okay, sorry. What I mean to say is you have backward elimination. Okay, backward elimination or forward selection. So forward selection means you start with one, okay, one column, okay, and then you keep adding another one, okay. Second, so that's called forward selection. Okay, so forward means you're going from 1 to n. That's what, right? When I say forward counting, you'll start counting 1 2 3 4. This is how you remember, right? So forward counting is like 1 2 3 4. So you start with one, you keep adding second, third, fourth. Okay, and this is little complex. Okay, I'll tell you why. Second method is backward elimination. Okay, backward elimination means you start with 5 and then you start eliminating one by one. Okay, so which is probably straightforward. Okay, then forward selection. Now let's say backward selection. Okay, we have these 5 columns, right? Now it says that do not remove more than one column at a time. Here you see the worst fit, okay, column or feature is x1, right? Worst fit is s1, highest p-value. So it says remove x1 from the model and then rerun again. Okay, okay, remove this one and rerun again. Again, check for the p-value. Because again, see, when you remove this, your model will be impacted, isn't it? So you may not see exactly same values here. Okay. So again, rerun the model. Again, okay. Then again, if you find something which is greater than 0.05, you remove it and again rerun the model. You keep doing that till you find all the columns having less than 0.05. Okay, so that's one. That's called backward elimination. You start with all and you keep eliminating one by one, and you come with a set of features. Forward selection. Why it is this thing is, now you start with one. Now when you start with one, which one to start with? Very difficult, isn't it?
Yes.
So that's why what you have to do is you have to take each of the 5. First step, you take x1 and c. Second step, you take x2. Third step, you take x3, so on. So you run each one individually, okay? Then you have to take two. Now again, which two? Again, you have so many combinations, 4 combinations probably. Then you take 3. Again, you take 4. Then you take 5. 5 is simple. You'll have only one combination. But 4, again, you'll end up getting 2 combination. Okay? So you'll end up getting multiple combinations. You have to run all these, and then based on your judgment, you will see, okay, x3 is always giving bad. Whether it is when you take only x3 also is giving bad, you take x3 with x2 also, it's bad. Okay? So so it says that probably x2 is first that we have to remove it. Okay, so that's why, okay, what we do, we ignore, okay, the columns which has higher p-value, and finally you'll come up with, okay, 4 or 3 or 2 or 1, okay, data set which is important. Now in this case, if you see here clearly, x1 is very high p-value,
Very
right?
high.
We need to
0.4.
remove. So we'll do backward elimination and see, okay? So we will start with, okay, removing x1.
Excellent.
We'll start with removing x1. So we go back, okay? Okay. We go back to here. So here we are taking all the x. So I'm going to say x equal to, okay, x equal to x of, okay, all rows, and I'm going to ignore the x1. So x1 means 0 will go away,
0 will not be okay.
isn't it?
Yes.
Right? So we'll remove 0. So I'm going to say here 0 gone, 1, 2, 3, 4. Right? Okay, 1, 2, 3, 4. Now you run it. Now you see here, x1 actually increased now. See, for us it is 1, 2, 3, 4, right? But this one,
Yes.
this
For
x1 is
example.
actually the first one, right?
Yes. Yes.
Now you see, first one has again higher value than p1. So I'll remove 1 also from here. Okay? This is higher than our threshold value. Threshold value is 0.05. So we'll run it again. Now you see, all these three have a p-value in acceptable
Less than
range.
ratio.
Right. So we say that these three, okay, which is your R&D spend, marketing spend, and I think second one is admin spend, third one is marketing spend. These three are the model which is important for us. Okay, so this is how we perform backward elimination and we select the model.
Yes.
Okay, so now you go back where here when we are doing X selection, right? So not only first one, we will drop 0, 1, and 2. Okay, 0,
Yes, 0,
sorry,
1.
0, 1,
1.
and 2. So by doing that, the state is completely removed. Right? Now you run the model. Okay? So I should not have done it. Wait, I should have done it differently so that, okay, 2, 3, 4. So here we have dropped anyway, right? So this index is anyway not there now, right? So what I'll do first, I'll first comment this part. Then we'll go here.
Hmm.
Okay. Column transform. Okay, I'll put the one only. And now I will say here something like this. After doing backward elimination method, we realized that all the region or state, right? This is the state. All the state columns are not significantly impacting the analysis. Hence, removing those two columns too. Okay. So now your X is going to be, now see X in this case, 0 and 1 is your column, right? So I'll say 2. Okay. So 0 and 1 will also be removed. So X equal to, okay, after backward elimination. So now you only have 3 columns to deal with. Okay. Okay. So you can check. This is the 9. It was 986, right? It became 987. Improved. And now this two are almost
Hmm.
same. Okay.
Adjust.
Yeah. So that means all 3 columns are significantly impacting. That's why even the best is also giving you 987 and all 3 together is also giving you 987. Now you can see your RMSE, all those things should have been increased. So this is how we, in the multiple linear regression, it is important to know which columns are important. Okay. And that's where your OLS will be able to help you. Important part. You can't go with, all the columns. You have to select your columns properly.
Hmm.
Right?
Yes.
Okay. Now there are a couple of other things also you should remember when you are doing it. Okay. Uh, we call them as um, um, uh, you know um, kind of we'll call it as how do I what do we call it? So we'll call it as let's say um, we'll call it test for linearity or something. Okay, what happens is when you're selecting your X and Y, okay, or your features and your target variable is no question, there is only one. But when collecting the feature variable, there are few tests that you have to perform. Okay, test number 1 is all features, okay, or X should be correlated to Y. Your X should be correlated to Y. If there is no correlation, there is no point of performing the analysis. Okay, that's one. Second thing you have to do is, okay, and there are many, there are 10 to 12. We can read them. Okay, it's there in the notes which I have shared. Okay, the notes I have shared, there are a lot of things with code, and you can practice all the code and things. Okay, it's okay, easy to understand. But what two things, okay, two important things that you have to understand here is your within features. Okay, there should not be any correlation. If it's there, then take any one for the analysis. Okay, so for example, you have a one column called car, number of cars, and second column is number of wheels. Now, number of cars and number of wheels both are X to predict something, let's say, your how much inventory you need, for example. Okay. Now, in this case, your number of cars and number of wheels, okay, are correlated, right? As you increase the number of cars, your wheels will also increase, isn't it? They're correlated. Then in this case, you drop one of them. You don't have to carry both. You drop one of them. You drop either car or number of wheels. Doesn't make sense to have both there. Okay, now you can decide whichever has a higher correlation with Y, that you drop. Whichever has a higher correlation with Y, whichever has the higher correlation that you keep. Okay, we want higher correlation, right? Isn't it? So whichever has the higher correlation that you keep, whichever has the lower correlation that you drop. Okay, so here there should not be any. Okay, and apart from that, there's some rules like your variables or X should follow a normal distribution. Okay, X should follow normal distribution. The error should also follow, okay, have normal distribution. Now this is called multicollinearity. Okay, what I'm talking about, this is called as multicollinearity. Multicollinearity. Okay, correlation is important, but multicollinearity is not. Okay, multicollinearity is within, variables. They exist multiple correlation. That should not be there. Okay, so these two things you will know. Okay, and there are few more which you can actually refer the notes and please, okay, check that. Okay, so this is called as multiple linear regression, and we have seen how to do the backward elimination. Similarly, you can do forward selection also. So forward selection, how to do? You have to do one by one. Yeah. Okay.